How's it going, everyone? Mr. Geyser here with the first video in our Lesson 14B series, where we've taken a look at logarithmic functions in the context of data modeling. When we have been able to fit data to logarithmic models using the regression feature natural log regression on our TI-84 calculators. But sometimes you'll need to find an equation without technology because the data has an x value of 0, or possibly because the data doesn't fit the logarithmic regression model. What I mean to say about this part here, when the x value of the data set equals 0, we can't plug in x equals 0 to our logarithmic regression models, like we'll see in example 5. Sometimes at those specific points, a different model is needed, but for the general trend of data, we can still use a logarithmic regression model. What I mean to say is, in example 5 here, a textbook publisher adds a new AP pre-calculus curriculum product to their sales category. On the very first day, where t equals 0, they sell a total of 14 of the curriculum to 14 different school districts. 21 days after the product was added, at t equals 21, the publisher sold the curriculum to 62 different school districts. The number of textbooks sold on a given day can be modeled by b of t equals a plus b times the natural log of t plus 1, where b of t is the number of pre-calculus curriculum products sold on any given day of t, since the new product was added to the publisher's category, their catalog. In part A, we want to use this given data to write two equations that can be used to find the values of those constants for a and b in this expression for b of t. Notice that t of 0, giving us the amount of products sold at 14, creates a unique point at 0, 14. Vice versa, with that next part there being t equals 21, we get that new point of 21, 62. Those 2 points are going to give us our two equations that can help us solve a and b. In the next part here, where we solve a and b, we'll be using a new method where we're subtracting these two equations from each other. What I mean to say is, in part B here, we want to find the values of a and b as a decimal approximation. We're first given b of 0 and b of 21, where b of 0 equals 14, that end result of 14 school districts buying the curriculum at 0 days, is equal to a plus b times the natural log of 0 plus 1. Same thing for that second point there, which is b of 21 equals 62. Those two equations, we can set them equal to each other by subtracting 14 on both sides on that first one, subtracting 62 on both sides, and setting them equal to each other. We could do that process like we did in the previous videos. However, I want you guys to see that if we place these two equations on top of each other and then subtract one of them from the other, making all of these signs opposite, subtracting 14 equals negative a minus b times the natural log of 1. Now, however, the natural log of 1 does equal 0 for us, pretty luckily, but we're just subtracting the equations from one another. I want you guys to practice solving out equations like this, because notice what happens to this a value. That a value between both of our equations subtracts out. And we're just left with 62 minus 14, which is 48, of b times the natural log of 0 minus 0, because the natural log of b times 1 in that previous version of the equation here, where really it's just 0 plus 1, that gave us 0 automatically. We end up getting this b times the natural log of 21 by itself on that right-hand side. I want you to try and practice subtracting equations from one another to try and get these single equations with a single variable. Whenever you have two variables, you need two equations to solve for those two variables. To solve for a single variable, you need a single equation. In this case here, it's pretty easy. We're just going to divide that natural log of 21 to both sides, and we end up getting b equals this 15.52741. Now that we know b here, we're able to plug b into any of those equations there. In my case, I'm going to plug it into that second equation, 62 equals, all that jazz, and we're ended up able to find a by itself. This here automatically just equals 48. We solved it in that previous problem. And we get a is equal to 14. Now that we know a and b, we're able to write out our whole b of t regression model, where it equals 14 plus that 15.5 decimal times the natural log of t plus 1. We can use this in our upcoming part C. We want to use the given data to find the average rate of change of the number of curriculum products sold from t equals 0 to t equals 21. we want to express this answer as a decimal approximation, and we want to show our computation that leads to this answer. Really, all we're trying to say in part C is what's the average rate of change of these 2 points. We know that the average rate of change equation is just that f of b is equal to f of a divided by b minus a. In this case here, we just needed those 2 given points that was at the start of the problem, where f of 21, or b of 21 minus b of 0 divided by 21 minus 0 really is the same as 62 minus 14 divided by 21, which gives us that decimal approximation of 2.2875 products sold per day. So every day it increases the number of products sold by 2.28. Meaning on t day 1, we'd expect to solve like 16.28. On t equaling 10, we'd assume that we'll solve like 30.6 or 30.7 books sold per that day. But this is the average rate of change between these 2 points. In general, we can use this in part D, where for part D, it states that we want to use the average rate of change found in part C to estimate the number of districts that will purchase the curriculum on day 15. We're going to show the work that leads to this answer. And really, in general, we're using this average rate of change of 2.2857 to predict how much or how many school districts will buy that curriculum at t equaling 5. We could kind of draw this out here in this semi-little graph where we're given this x and y, where the x is the number of days that we have for the problem, and y is the amount of curriculum sold. In general, when we're given 0 as a point, it's really difficult for us to use a logarithmic regression because when we plug 0 into any logarithmic regression, we're going to get some vertical asymptote answer, or really some discontinuity where it's approaching that 0, but it's never reaching it. In this case, when we use that average rate of change, we're really just creating a single line between these 2 given points and then adding this formula for this rate of change model. This rate of change model is linear. And really, we can find this to be some f of x is equal to m times x plus b. Really, that m is just going to be the slope for that average rate of change. So on a linear model, we would state that when the x value is 15, the slope between these 2 points here would be 2.2, and that b is really just the y-intercept, whereas x equals 0. So we can find that when f of 15 for our linear model, it's going to be right around 48.2855. However, let's explore how close this linear approximation is compared to the logarithmic approximation. The logarithmic approximation was that b of t that we solved before. So in part E, let a of t represent the estimate of the number of curriculum products were sold using the average rate of change found in part C and D. Let a of 15 be found in part D. It can be shown that a of 15 is significantly less than b of 15. Explain why, in general, this a of t is less than b of t for all t, where it's greater than 0 but less than 21. What I mean to say is, for our average rate of change at t equals 15, we get around 84. But in our regression model for logarithmic, that b of t, when we plug 15 into that ln, we end up getting like 57.0546, significantly higher than this prediction here. What we want to claim is that for this difference between the regression model and the predicted model here, we're stating that this purple line here is the actual given data set, where at 15, we have this difference, this residual between the 2 graphs. And when we want to describe the residual between these 2 graphs, we use that equation of y, the actual data for purple, minus y hat, the predicted data created by that average rate of change. When we create this difference here, what we can specify is that the estimate of y of x lies on the secant line below the given b of t function. This underestimates the data. The reason why a of t is so significantly less than b of t is because it's an average that underestimates the data. We have this increasing at a decreasing rate between these 2 points here. So when we create an average rate of change secant line between these 2 points, it's always going to take an underestimation regardless of where that second point is. We can explore this further in our next couple examples. In example 6, the function h is increasing. The table below gives the values for the function at any selected x value that's given. A logarithmic regression model of y equals a plus b times ln of x is used to model this data here. In part A, we want to find that logarithmic regression model. To do that, we just want to bring in these 5 data points into our TI-84 calculators to calculate out what that regression model is. To do this, we're going to our TI-84. We want to hit stats. On stats, we're going to hit that first option for edit. This first option, edit, is going to allow us to plug in those x and those y values. Those x values there that we're plugging in is going to be that 0.2, hitting enter, 1.3, 3.7, 6.2, and 10.4. Once we bring in our x values into our L1 list, we're going to bring in those y values in our L2 list, negative 3.4, 1.9, 5.1, 6.5, and 7.9. Once we have our x and our y values here, we're going back to stats, over to calculate, and using that 9th option for linear regression. Once we have this, it auto-selects L1 and L2 for our x and our y list. Some students may not have this screen, but it's still the same process regardless. We're tabbing down to where it says store regression equation. For those that don't have the screen, all you do is select variables, tab over to y variables for that first function for y1. Now everyone here is storing that function for our regression model in y1, where our a is that 1.22 decimal and our b is that 2.87 decimal. We can bring in our a and b into our guided notes here and saying that h of x is equivalent to this regression model. We can use this in part B, where we want to use the logarithmic regression model to predict the values of h when x equals 4. To do this, we could manually plug in this x equals 4 here right into this regression model, where we're plugging 4 into that natural log, or we can do a little shortcut. On our TI-84s, I want to go into the table where x equals 4. To do this, I use that shortcut to hit second and table set, and I'm going to have my table start at 4, where x equals 4. And when I hit second table above graph, it goes to right where x equals 4, which is 5.21429. It automatically gives me that value, which I can bring into our guided notes, where h of 4 is equal to that 5.2 decimal. Keeping that in mind for part C, what is the residual for the data value at 3.7, 5.1? What this question is asking is that this here is a given data value from our table. This is the known actual value of x and h of x. But according to our regression model, 3.7 gives us, let's check that table real quick. Going over to that quick shortcut, second table start, 3.7. Going back over to our table, it gives us a different fraction, or sorry, it gives us a different decimal, 4.90498. We get some lower number than the actual value here. That difference between those values there creates some residual between our y and our y hat at specifically x equals 3.7. At x equals 3.7, our known value of y is 5.1. The residual plot predicts that it would be 4.989866, which gives us a residual of 0.110134. In general, these decimals aren't really what we care about. It's the fact that this number here is positive. When we have a positive residual, it means that that is underestimating this value here. And it's kind of easy to see that. Our regression model gives us a smaller number than the actual data, so it's underestimating at that specific point. If this number here for the residual was a negative number, it means that this value was larger than the actual data set, meaning that any negative residual is overestimating and any positive residual is underestimating. Now let's take one final look at part D, where in part D we want to use the model to predict where h of x equals 9. Now where h of x equals 9 is different than when we're plugging in the value of 9 into where x is. What I mean to say is if we go back to our data set here, I want to know when y1 is 9, not when x equals 9. And in general, I can tab down just a little bit to try and find right around where it equals 9. And I'm tabbing down and I see it happens between 14.7 and like 15.7. I don't know exactly when my y1 will equal that. So I can use that intercept trick where I'm going to y equals, for y2, I want to make that equal 9, and I want to go to that window where those two lines are going to cross. Well, according to my table here, it's going to happen between the x values of 14.7 and 15.7. So I can change my window here where my x minimum is going to be like 13, and my x maximum has to be over that 15.7. So I make that equal to like 16. For my y minimum, since I know I want to hit 9 for my y1, or for my y minimum, I'm just going to make it 8, like 1 below it. And my y maximum, I'm going to make it y equals 10, about 1 above it. So I know when I hit my graph, I know exactly that I'm going to go to that intercept. At that intercept there, I'm using my second for calculate, right above that trace option, going to that fifth option for intercept, selecting those two curves there, first that blue one, second that red one, and then I'm just tabbing right around where that intercept's going to be. And my guess here gets me really close to that intercept of 14.900102. So when x is 14.9, I get the value of 9 for my y there. And what I mean to say is, when h of x equals 9, really it's h of 14.900109 that gives me that 9 as my answer. Thank you very much for joining me on this first video for Lesson 14b, where we found these regression models from a given data set and used that intercept trick to find when these y values are given to a specific x value. Thank you very much for joining me, and I look forward to seeing you guys in that next video. Take care.